Hi everyone, my name is ABDrake and I'm a postdoc currently working at MPIA in Heidelberg. And this is my recorded talk, third attempt, for cosmic gas and the first quasars at redshift 6. And I'm working here as part of the high redshift quasar team led by Fabian Walter and a host of other luminaries in the field. Okay, so talking about quasars at and above redshift 6, I'm focusing on objects in the first gigayear of the universe. And these quasars allow us to directly observe young, massive, active galaxies and their rapidly accreting supermassive black holes. Now, one perk of studying these objects is that actually the ionizing radiation from the QSO illuminates the surrounding gas and therefore allows us to study the quasar's circumgalactic medium in emission. But it's only in more recent years that we've started to be able to observe the actual ISM of the redshift 6 QSO host galaxies, for instance with ALMA. And so now I want to talk about putting the pieces together about the gas flow in and around quasars at redshift 6. Excuse me. So Lyman alpha halos around quasars have actually been sought after for some time. And there's a series of heroic efforts in the literature going as far back as 2006, where people would use long slit spectroscopy or narrowband imaging to search for any kind of sign of extended Lyman alpha emission surrounding a QSO. But really the game changer in this particular field came from MUSE, which is the integral field spectrograph installed on UT4 at the VLT. The first major player that came out in this field was the Borisova paper in 2016, where they went in and looked at a series of the brightest quasars they could find in the sky and looked for extended Lyman alpha. The big surprise being that not only did some of them have Lyman alpha halos, but they all did, and they were all ginormous, extending somewhere up to like 100 kiloparsecs. Hot on the heels of this was the QSO Museum survey led by Aragoni Batea, moving further down the list of brightnesses for QSOs, and again, lots more halos, adding about 60 more objects to the parameter space now. Then also in 2017, there was an important paper from Emanuele Foina, who found the first MUSE detected Lyman alpha halo at redshift 6. And this thing was very tiny and quite faint, and I know that he had to do some, a lot of data processing to actually detect and confirm this halo at all. So, motivated by these studies, in particular Emma's paper, last year I delved into the ESO archive to dig out all of the quasars at redshift 6 which had been observed with MUSE, and so looking for publicly available data, and I restricted my sample to objects that had been observed for more than 2 hours. So out of 5 quasars that we found at redshift 6, 4 of them are showing extended Lyman alpha halos. And so in my 2019 paper, I've gone to some efforts to characterize the halos and then to put them in the context of other objects across cosmic time. So to summarize the properties of these halos as quickly as I possibly can, I would say that they're all large, spatially asymmetric, and they're exhibiting high velocity widths. The areas on sky of Lyman alpha emission above 10 to the minus 17 in surface brightness range anywhere between 6 and 18 square arc seconds, and their sizes are between 2 to 5 arc seconds, which corresponds to 12 to 29 proper kiloparsecs at redshift 6. And again, they're all bright. Their log luminosities are between 43.3 and 44.4 ergs per second. Indeed, if they weren't bright, then we would have had great difficulty seeing them at all. So, with respect to the internal halo kinematics, I'm now talking about the moments of the halo gas relative to the peak of the Lyman alpha emission from that halo, so no longer relative to the systemic redshift of the QSO. we see some interesting signs of some kind of ordered motion in the Lyman alpha halos. In the paper, I was deliberately restrained in my interpretation of this because really with the Lyman alpha alone, it's difficult to say what we're looking at due to the complicated radiative transfer effects. When it comes to the second moment, the velocity dispersion, the values are typically a few hundred kilometers per second, but in the radio loud object, which is the top two panels there, there's a larger area of a higher velocity dispersion, as one might imagine. So with respect to the halo's luminosity evolution across cosmic time, before my paper last year, the right-hand side of this kind of plot was rather sparsely populated. There are a couple of upper limits from DeCarli et al., which I haven't put on the plot because I'm showing here only halos that have been observed with MUSE. But what we did have was a nice halo at redshift 5 point something from Ginolfi et al. And then there was the Farina halo at redshift 6.5 or something, which, as you can see, was very tiny and very not particularly luminous. So in our paper, we added these 4 points to the plot. And as you can see, it already kind of transforms the way that we view the evolution of these systems. And following that, there was the Requiem survey, again from Farina et al., where he filled in the rest of the parameter space over here very nicely. And this was a snapshot survey with a large program on MUSE. So each one of his snapshots was only an hour long in exposure, which is why some of these are upper limits. And I know that Emma is convinced if he were to expose a little longer, he might actually detect significant halos for all of these objects. Let's see. There's also a nice paper from Mamose et al., which I encourage you to look at, which tackles similar questions. So I won't focus on the rest of the 2019 paper right now, but there's a couple of other nice results which I would encourage you to have a look at. We looked at the surface brightness profiles and the origin of the Lyman alpha emission, finding that stuff was coming from within the virial radius, so we were really probing the CGM, and these weren't intergalactic medium emitters. We also had a look at the Lyman alpha powering mechanisms, but really all of this was speculation, which is always my favorite thing to do, but one has to remember it is speculation. I've put the links to the paper up here if that's of interest for you. But what can we say about systems where we actually can see the ISM of the host galaxy? Will this help us to understand the bigger picture and the link between the galaxy and its Lyman alpha halo? So this is where the system BR1202 comes into play. BR1202 is a QSO SMG major merger at redshift 4.7. It also happens to be the object pictured on the bottom right of the screen, which has been artistically adapted by PowerPoint. This is HST imaging. So when you look at BR1202 in HST, it looks like a fairly innocent QSO with a couple of blobby things nearby that one might, speculate could be other objects at the same redshift as the QSO. And 2 of these were reported as being Lyman alpha emitters, usually from narrowband imaging. And yet it's only when we go to the submillimeter that it becomes obvious that BR1202 is actually a major merger system. And in the top right, there's this massive submillimeter galaxy, which is completely and utterly optically obscured. Note that it's separate from the fuzzy optical blob, which you see nearby that position. So the paper, which I'm just about to resubmit following the referee report, is entitled Kinematics of Cool and Ionized Gas in BR1202. What I'm showing in the top right corner right now is this animated GIF of the extended Lyman alpha emission in the BR1202 system. And as you can see immediately, there is a beautiful extended Lyman alpha halo, which is very large on sky. Another very obvious point to make, but it's interesting to note how different the morphologies of this system are depending on which wavelength you're looking at. So I'm showing in grayscale here the original HST imaging. I've overlaid those dust continuum contours from ALMA in red, which I just showed you. And then on top of that, we have an indication of the significance of the Muse Lyman alpha emission, all of which appear to be tracing very differently set up systems. A nicer way to look at the Lyman alpha halo is to take a narrow velocity slice in the middle of the peak of the emission. And you already see that all of these objects pop out, and yet there doesn't seem to be any Lyman alpha emission originating from the position of the SMG, which is fascinating given that the SMG and the QSO have got very similar far infrared luminosities and similar obscured star formation rates. Finally, there were some interesting indications that came from the ALMA commissioning data led by Kirilli 2013. There's also a paper by WAG 2012 where they propose that there's actually a bridge of C+ emission between the QSO and the SMG. And actually, when we look at this together with the new Muse data, we find that there's a certain amount of kinematic coupling between the C+ tracing the ISM, one might imagine, and the extended Lyman alpha halo, which really is indicative to me of some kind of merging event where everything's being torn apart. Okay, another perk, I've used the word perk too many times, but it's another perk of the Muse data that one can serendipitously discover Lyman alpha companions within the cube. So here I'm presenting LAE3, which was a nice Lyman alpha emitter which just popped out of the cube without even looking for it at approximately 300 kilometers per second away from the QSO. We measured the equivalent width of the Lyman alpha emission, although we had to place a 5 sigma lower limit given that the LAE is not detected in the Muse continuum, or rather its stellar continuum is not detected in the Muse cube. And its flux translates to a modest star formation rate of approximately 5 stellar masses per year. And notice that this LAE is completely undetected in both C+ and the dust continuum, which is kind of typical of these presumably low mass, high redshift star forming galaxies. Another nice thing that we could do in this paper was to refine the definition of, and in some cases redefine, the nature of the objects which had already been reported from narrowband imaging. So for LAE1, which is this optically seen blob partway between the QSO and the SMG, its position is defined according to the C+ peak from the Chris Kirilli's paper. And actually the optical and the submillimeter peaks are offset on sky by a couple of arc seconds. Likewise, the Lyman alpha and the C+ velocity offset is approximately 400 kilometers per second. And this object seems to have a fairly large Lyman alpha equivalent width of approximately 72 angstroms, which is consistent almost with previous measures in the literature. It's a large equivalent width, but it's not impossible that this is driven by star formation still. On the other hand, LAE2, which is defined as being this blobby thing towards the bottom right, position defined in the submillimeter again. But when we look at the Lyman alpha emission, we actually find that there's no local peak as you step through the slices of the Muse cube, which implies to me that LAE2 is actually not an LAE. This is obviously some kind of embedded object within the Lyman alpha halo, where the previously reported Lyman alpha line at this position is actually just part of the QSO's extended halo, which is covering the position of this object. Okay, so how can we go about connecting the Lyman alpha halos to their host galaxies? I'm now going to talk about a small sample of QSOs at redshift 6 where both Muse and ALMA observations exist, allowing us to link up Lyman alpha halos with C+ emission from the host galaxy ISM. So for 6 of these objects coming from the surveys led by Roberto Giacali and Emanuele Farina, I want to emphasize that I'm focusing here on objects which have definitely shown A, a Lyman alpha halo, and B, C plus emission. So I'm only comparing objects here where both data sets not only exist, but the object is detected in both data sets, right? So for the objects where we look at these Lyman alpha halos, this is what I'm showing in the upper panels. These things are fairly extended on sky, and one finds that we have to actually zoom in quite a lot to put the C plus emission on the same scale. So in the upper panels, I'm showing a 10 arc second cutout, and in the lower panels where I show the C plus emission, I'm showing a 4 arc second cutout. So the Lyman alpha is much more nebulous and extended than the C plus, which is a rather obvious statement, but it's worth noting, especially because they're actually, co-spatial on sky. And we're finding that, the C plus is coming from the region which we actually have to block out in the PSF subtraction when you're looking for the Lyman alpha halo. Okay, so while the Lyman alpha halos are becoming routinely detected, more or less at high redshift, the radiative transfer of Lyman alpha photons leads to messy kinematics, as I've said before. Whereas ALMA is providing spatially resolved host galaxy properties, including rotating disks. I know there's a lot of references in the literature for this, and we've seen some great talks on it this week as well at SAZERAC. But I'm pointing here specifically to Marcel Neylemann's paper, where he's shown a nice rotating disk at redshift 4 point something. And this is really motivation to try and connect these two alternative views of the universe in emission by looking at their morphology and their kinematics. So I've made a comparison of Lyman alpha and C plus moment maps for the 6 quasars that I showed you before. And we want to ask the question, are the kinematics of the two components part of the same structure? So if the Lyman alpha is showing some ordered motion, does this match the rotation of the galaxy's ISM? Are we just looking at a giant gas cloud which is collapsing in on itself? One nice example in the literature is the Prescott et al. Paper in 2015, where they've found some signature of rotation in the extended Lyman alpha halo of a quasar at redshift 2. In this case, I'm showing you here P308, which is another famous merging system at redshift 6. Take a look at Roberto Di Carli's paper on that. We see absolutely no coherence whatsoever between the first moment, which is the velocity structure in the Lyman alpha and in the C plus. What's perhaps even more interesting are these two objects here, P231 minus 21 and P036 plus 03, because the velocity gradient seen in the Lyman alpha is actually perpendicular to that seen in the C plus structure. So this is absolutely intriguing and really sets us up for, an exciting investigation into what exactly is going on. Okay, so my summary warning now, there are 2 summary slides. I wanted to emphasize that we discovered that there are large and bright Lyman alpha halos existing at redshift 6, and that's reformed the way that we're looking at this field now. In the redshift 4.7 major merger BR1202, we've reported the existence of a giant Lyman alpha halo and the kinematically coupled C plus emission between the QSO and the SMG. And yet when we look at a series of quasars at redshift 6, we find that the velocity fields between the host galaxy and the Lyman alpha halo are somewhat disjointed, which sets us up for intriguing investigations in the future. Final slide. For me, this absolutely means JWST. There's so many unanswered questions left in the field. The powering mechanisms of the Lyman alpha halos, the kinematics of the halos, and their relation to the host galaxies. Now we know that to some extent Lyman alpha means H alpha, and H alpha means prizes. Certainly H alpha means answers. And so it just so happens that these quasars fit almost precisely into 1 or 2 near-spec IFU pointings where we can target H alpha halos coincident with the Lyman alpha halo. I'm sure that's entirely coincidental. However, they make ideal targets for follow-up with JWST, and I'm really excited about trying to go forward with that. So that's all I wanted to say. Thank you for listening, and I'm sorry that I hit 20 minutes again. But if you're interested in talking to me or seeing what's going on, please follow me on Twitter or have a look at my website. And thank you very much for listening.